Yes, good morning. I'm starting today with the topic three-dimensional transformations. As we already studied two-dimensional transformations, which includes translation, scaling, rotation. These three are a major transformation functions which we use. With this, the additional transformation functions were shearing and reflection. So all this we have learned with respect to 2D transformations. So today we will learn the same thing with respect to 3D transformation, just one by one. So 3D transformation, the first one, we will, before going to any of the transformation functions, we will see, we'll just learn about the basics of three-dimensional transformations. So here, use homogeneous coordinates just as in 2D. We already used homogeneous coordinate system in two-dimensional transformation functions. In the same way here, we start using homogeneous coordinate system. We also learned what is homogeneous coordinate system, right? So when it comes across a homogeneous coordinate system, the transformation will be of 4 cross 4 matrices, which represents 4-element column vector. In this package, we are learning column vector. What is the column vector? My value starts storing in the form of a column first. So it goes like this. Yeah. So this is a column vector. The value stores in this way. And one more point is, we will use a right-handed coordinate system here for our easy purpose. So that's nothing but our Z will come out of the page here. So you're able to see the Z axis. If we imagine that the Z actually comes out of our screen or out of our page, if you're drawing this on your sheet. Why do we call it as a right-handed coordinate system? Because you can hold your right hand as well as your left hand now, currently in front of you. Always the x-axis will be towards your right side, and the y-axis will be the upsides. Any coordinate system, as you know, whether it is a right-handed or Cartesian coordinate system that we are using here, or left-handed Cartesian coordinate system, in our Cartesian coordinate system, always we will plot like this, the x and y. Our minus x minus y will come in the other way, but our positive x and positive y will always be like this. That means x will be in the right-hand side and y will be projecting or facing towards the upward side. So now you keep both of your hands, both your right hand and the left hand. Place your thumb towards the direction of x. Place your forefinger towards the y-axis, that is upward. And check your middle finger. Keep your right hand side and place your thumb towards your x-axis, that is always will be a right side, and your forefinger to the upward, and try to get your middle finger. Give a position to the middle finger. So middle finger is coming towards which direction? Is that coming towards you? So that is what, when you see in your right hand side, it is coming, the middle finger is coming towards you. In the same way, keep your left hand side, thumb placing your x-axis, that is your right side, forefinger placing your y-axis, that is your up side, and check with your middle finger where it is placing. It is placing away from you, that I'm writing here on the right side, away from you. This will be your left hand coordinate system. This is your right hand coordinate system. Hope you have got it. So here we are actually taking a right hand coordinate system for all the example, because we are able to see the image very clearly if we take the right hand side. When we are putting this on the, what I can say, on the book or for the explanation. But please note it, when you are executing this on the screen, or when you're typing your programs, see to that your left hand side will be a better option, because analyzing or placing in the screen away from you, the object is placing away from you, will be analyzed better compared to the right hand side. So that's why they say that when you project onto the screen or to any device, see to that it will be left hand side. Currently we are actually studying here, we are drawing here, that's why we have taken the right hand side. So this is our basic, that I am taking my coordinate system, that is a right handed coordinate system. Fine. The first transformation functions, we deal with the translation. So what is a translation function? The translation function, we already know that the object is moving from one place to the other place, is nothing but a translation function. Okay, the object is moving from one place to the other place. So now let us consider P. Point P is an initial point, and P, it is completely similar to our 2D. Only thing is we are adding our Z coordinate here. Everywhere you can see we are just adding the Z coordinate system. So if P is equal to XYZ, then a new point P dash will be X dash, Y dash and Z dash. Then how much distance you are traversed, or the displacement I call it as, from P to P dash, we put that in the terms called Tx, Ty and Tz. That is my translation term. So what will be my X dash then? X dash will be my current position, and how much you are moved will be my X dash. Y dash will be my current Y position, and how much you need to travel is my Y dash. So it's very simple when it comes to the Google map. You will put your destination where you want to go. That's nothing but how many kilometers you need to travel. Starts from your current position. So the current place plus how much of kilometer you need to traverse will be your destination. So like that, we will check for all three dimensions, that is X dash, Y dash and Z dash. So this is our three-dimensional translation formulas. How do we express in the matrix form? We express in this way. We already know, we have just done in two-dimensional matrix, where we don't have only the Z part. Leaving this part, that will become our two-dimensional matrix, two-dimensional translation matrix. Now we are seeing three-dimensional translation matrix, where we will have a Z coordinate. So we have added a Z coordinate here. We have added the Z coordinate here. So now See here, they have given a drawing here. This is your P point, where you need to travel to your P dash. To go to this P dash from your point, how much you need to travel, this will give me translation parameter, that is T. T includes how much you need to travel with respect to x-axis, how much you need to travel with respect to y-axis, and how much you need to travel with respect to z-axis. Everything will be your T. Each and every point give me, as I have now 3 axes, x-axis, y-axis, and z-axis, my point P will have all 3 values. Do you agree that? A point P will have all 3 values. That is nothing but, if P will have x, y, and z. Fine. Which position with respect to x, which position with respect to y, and which position with respect to z. All 3 values should be there. So that means how much I need to travel? Obviously, how much I need to travel with respect to x coordinate, how much I need to travel with respect to y coordinate, and how much I need to travel with respect to z coordinate. Everything is my dx. I need to specify individually. That is my translation. So now you can see an object here very clearly. The object is here, initial point. It has moved to the P dash, a new point. What is a distance that it has traveled? Is this distance, T. If I add that to my current object, then I can move, I'll get the position of the new place where the object must be placed, or it is placed, already placed. So my general formula will be P dash is equal to T into P. What will be my P? My P will be my x, y, z, that's a current point. What will be my T? The T will be my matrix. That's nothing but our T will be our 4 cross 4 matrix. Is that clear? That I call it as a translation operator. Hope you have understood about the translation. So next we will go to 3-dimensional rotation. So 3-dimensional rotation, we can rotate an object about any axis in space, but the easiest rotation axis to handle are those that are parallel to the Cartesian coordinate axis. So what they're saying here is, when it comes to the rotation, you don't have to rotate with respect to your axis itself. You should have a freedom to rotate however you know, however you can. That is nothing but an arbitrary rotation that is independent of your coordinate axis. You'll come to know what I'm actually trying to tell here. So they're saying that you can rotate anywhere in the space. Not necessary that always you need to rotate with respect to the coordinate axis. That's my first point. Please remember this point. We will use this later. Also, we can use the combination of coordinate axis rotation to specify a rotation about any other line in space. So they're saying we are going to learn this in further, but currently, as this is little complicated, which is easy, that is rotating with respect to your coordinate axis. Let us consider that first. Okay, let us learn that first, and then we will start calculating with respect to the other axis. Okay, so that means I have a coordinate axis x, y, and z. Okay, x, y, and z. Rotation with respect to this axis, with respect to this, yeah, that is what we call it as a rotation with respect to the coordinate axis. If I have some object, but why I have to deal with this axis itself? I can rotate however I want. independent of this axis. I just wanted to rotate here itself. Fine. That's the point here. So, but this point is actually a little difficult. So before directly going into this point, we will check how do we rotate with respect to the coordinate axis, which is little simple. We'll learn little simple one first, and then we will go to the next one. So that is having a other axis. By convention, positive, yeah, we have already seen this. What was our by default rotation angle, whether it will go clockwise or anti-clockwise? I think you have remembered that it will go anti-clockwise, right? So that means whatever my rotation with respect to theta I had, the theta was positive when I was rotating it as anti-clockwise, right? Remember that? If I want to rotate that clockwise, then my theta was inverse of my actual one. That will be minus theta. My angle will be negative when it is clockwise, when I try to rotate it clockwise. But my angle is positive. When the angle is positive, then it rotates anti-clockwise. So that means my default rotation is with respect to the anti-clockwise, where my theta is positive. Okay. This we have already learned 2D. So this is my convention. This is by convention. We are assuming this in further also. That means we are going ahead with the positive rotation angles which produce counterclockwise. That is an anti-clockwise rotation. That is by default. Need to specify which axis. This is very important. Now, as we have already told you, I'm going to rotate the objects with respect to the coordinate axis. How many coordinate axes I have? I have 3, X, Y, and Z. So when I have 3, altogether, I can't use all 3 axes. Using all 3 axes, I can't rotate. So that means using a coordinate axis, if I want to rotate only, based on one at a time, each axis I need to rotate. Fine. So that's why they say that we need to specify which axis the rotation is about, in which axis I'm rotating, whether I am rotating with respect to Z axis, or I'm rotating with respect to X axis, or I'm rotating with respect to Y axis. So this is what we need to check. So that if I want to see that, then I have to specify which axis I am rotating. This is just, I will tell you later, you will understand how it is. Our 2D case, in 2D case, whatever the rotation I had, so I think we assume our 2D was only this much, right? Only this much was our 2D. We didn't had this, right? So our 2D rotation was cos theta. Please remember, recollect this, minus sin theta, cos theta, right? So that means I didn't had my Z axis here. So what was my X dash? I'll recollect. It was X cos theta minus Y sin theta. Y dash is equal to X sin theta plus Y cos theta. So that means if this matrix gets multiplied with X, Y, and Z, what will be my X dash, Y dash, and Z? Sorry, 1. Homogeneous. So that means multiply X cos theta with X. X cos theta minus Y sin theta. 0 into 1 is actually 0. X into sin theta plus Y into cos theta plus 0. So this is what we got. You remember this? Fine? Fine. So now let us go back. Go to the next slide. how the rotation happens. Let's remember this. We'll come back to this. Okay, we just recollected our 2D, two-dimensional case here. We will come back to this. Now let's think of our 3D. So what did I say? The rotation should happen around each and every coordinate axis. If it is each and every coordinate axis, then how it is happening here? You can see the diagram here very clearly. I have x-axis. Fine. Now, how the rotation usually happens? Keep your thumb towards any axis. Now here, the axis rotation is happening with respect to, it is given here, with respect to x-axis. So in whichever the axis it is rotating, place your thumb towards that axis and use all your other fingers. Starts to rotate. In which angle it is rotating? The other fingers direction, in which angle, in which side, the direction, the other fingers apart from your thumb is showing, that will be your direction of rotation. Is that clear? That will be your direction of rotation. So that means place your thumb towards x-axis. Now, because we are rotating with respect to x-axis, place your thumb towards your x-axis. Now check all your other fingers. See in which direction they are pointing to. In that direction, the rotation will be axis. Now, which is the first axis it is coming across? When you're placing your thumb on the x-axis, please see which axis it is coming across. It is coming across y-axis first, followed by z-axis. Correct? Correct? Okay. Now, see your y-axis. As it is rotating with respect to the y-axis, your direction is towards the y-axis, right? Now place your thumb towards the y-axis and check your all other 4 fingers in which direction they are showing you. You just bend those fingers. Don't keep it straight. Bend it. So that means showing your rotation. Bend it. Fine. When you're bending all your fingers, just in which direction it is rotating? It is passing the first axis. Which axis? Z-axis, followed by x-axis. In the same way, when it comes across z-axis, place your thumb towards your z-axis and check. Try to fold your fingers and then check in which axis it is passing first. It is passing x-axis followed by y-axis. Is that clear? Z-axis followed by x-axis. Okay, so the direction flow from the z-axis to the towards, it will go to x-axis. In the same way, z-axis. Z-axis is like this. I'm placing like this. Now check my thumb. Okay, so how it is coming? This is my x-axis actually. I'm touching my x-axis first and then going to y-axis first. Okay, so when it is towards the z-axis, I'm touching x-axis first, rotate it. So it is rotating like this. This is my x-axis. This is my z-axis. Yeah, I'll keep green to the x-axis. Green is my x-axis. So I'm touching x-axis first and then I'm going to y-axis. I'm touching x-axis first and then I'm going to y-axis. So that means when the rotation with respect to z, Andre, which is that axis it is touching first? X-axis, and then it is going to y-axis. Hope it's clear. Okay, now we will go and see the calculation part. What will be the rotation? So now all different axes the rotation is happening. So that means my rotation formula changes with respect to the axis. So we will see the rotation formula now. Fine. Now we will see rotation. Okay, we have done with this, right? So now we have understood with respect to x-axis y to z, y-axis z to x. Okay, we will see that now. Now, this is again a proper view for you how it is rotating. Again, they have shown here. Hope you have understood this. Directly, I will go now. Rotation with respect to z-axis. The first one we will take rotation with respect to z-axis. Now, whenever the rotation with respect to z-axis, now the two-dimensional z-axis rotation. So when it is z-axis rotation, I will have my x dash, y dash, z dash. Fine. When it is z-axis rotation, it is going to which axis first? Rotation x first, followed by y, right? But z remains z itself. My new value of z is nothing. It is z itself. It remains z. There's a constant value. Whatever I had z value, it remains as it is. Z dash will remain z. But when it goes to now, which is the first axis it is rotating? Going for the rotation x-axis. So write the formula. What is my formula? It is going to x-axis first. So my formula is x cos theta minus y sin theta followed by x sin theta plus y cos theta. That remains as it is. This I call it as equation 1. Okay. So that means this is what is said here. See, this formula is nothing but, I'll just tell you what is this after writing the matrix. I think our matrix is next. Yes, fine. So now parameter theta specifies the rotation angle about the z-axis. Yes, we already know that. And z coordinate values are unchanged by this transformation. That we have understood that z coordinate values are unchanged. I'll go to the next slide now. Then how do I write in the form of a matrix form? So that means that we have to include homogeneous. X dash y dash z dash 1 is equal to x y z 1. So what was my formula? X cos theta minus y sin theta. So this 2 will be 0, right? I don't have a z here. Z is same, followed by x sin theta minus, plus cos theta 0, 0. So this is a column vector. So this will be your x, this will be your y, this will be your z, and this will be your homogeneous coordinate system. This will be your homogeneous coordinate system. Then followed by, I don't have a z. So z, I should have z itself. That is 1, 0, 0, 0, 0. Sorry, is this 1? No, this is not 1. If I make this 1, then x, it will become x. Where I should make 1? This is 1. I should get z. 0, 0. This is my homogeneous coordinate system. Now you can see this. Actually, this part is my two-dimensional, right? This part is my two-dimensional. So let's go back and check our two-dimensional. See here. Why it was two-dimensional? Because we didn't have z axis in two-dimensional. So we made z-axis nil. So that's why constant. So that's why x and y it is rotating. So that's why we said z-axis rotation is the same as 2D case. Whatever the 2D default rotation you will take, that is nothing but our z-axis rotation in your 3D case. Okay, see. Okay, this was your formula in 3-dimensional. Fine. Now, which we can write more compactly as, how we can write? P dash is equal to, what is this? Rotation with respect to z-axis. Rz of theta into P. Theta is a positive here. Hope you have understood this. I'll go to the next one. Please make a note. I just forgot to tell the translation inverse. Translation inverse is same as here, 2D inverse. T inverse is nothing but here, T of minus Tx. It will be minus everywhere. Tz. Okay, this is your T inverse. Fine. So we'll come back to P dash, Rz of theta. Now we'll go for the next one. Now we will see with respect to the other two coordinates, which is obtained with cyclic permutation of the coordinates, parameters x, y, z in equation 1. So we will take the same equation 1. We will start with the cyclic order. Okay, you'll come to know. Thus, to obtain x-axis, y-axis rotation, we have a cyclic replace. So we will see this replace, how it is. So the equation for 3-dimensional x-axis rotation. So what will be now x-axis rotation? I'll just write it here itself instead of going back. X, y, and z. If you want to rotate with respect to x-axis, which axis first comes first? Y, right? Followed by z. Y-axis followed by z-axis. So now, how do you write an equation? I need x dash, y dash, and z dash. What is x dash? Now I'm rotating with respect to x here. So when I'm rotating with respect to x, x will be constant. That is x. What will be y dash? Keep the same formula. What was our formula? X cos theta minus y sin theta. X sin theta plus y cos theta. Replace it. That time we rotated with followed by x and y. Now we are rotating with respect to y and z. So all my x will be replaced by y. All my y will be replaced by z. That's all. So that means my formula now is y cos theta minus z sin theta followed by y sin theta plus z cos theta. Hope you have understood. Hope you have understood this much. I'll write the matrix form here itself. A homogeneous matrix form. It will be easy for you as we have already have a place here. Let's write it here itself. The homogeneous matrix form will be x dash y dash z dash 1 equals to, this is my rotation matrix followed by x, y, z, 1. So what will be my x? X remains x itself, right? Sorry, x remains x itself. So what will be that? 1. Because I'll multiply, x, 1 into x is x. Plus everything else is 0 here. So I'll keep everything else 0. Now y part. Y is this side. Y is this side. X is this side. All my x is 0 here. So aram se you can make it 0, 0. Okay. Now, what is y? I'm dealing only with y and z. So what is y? Y is here. Y cos theta minus sine theta. This is sine theta cos theta. 0, 0, 1, 0, 0, 1. So this is my final. How do you generalize it? P dash equals, okay, P dash equals, what is this? We call it as rotation with respect to x, theta. How much angle? By an angle theta along x-axis into P. This is my generalized. So use the same statements what we have used for the z-axis. Hope you have understood this. Fine. Let's go to the next part. Please give a message to Josephine ma'am. Here I'm not able to see. If you want me to repeat it, any case. Shall I go ahead?
Yes, Priya, you can go on.
Fine. This is x-axis. We have seen this. We have seen all compact everything. That is nothing but our matrix form as well as generalized form we have seen. Now we will see with respect to y-axis. So what happens with respect to y-axis? So y-axis, I have x, y, and z. So it is rotating like this. So which one it is crossing first, coming across? It is coming across. Oh, sorry, we are in y. We are in y. We have done with z, right? We are in y. We are done with z. This is my y. Rotates like this. So in y-axis, which rotation? Z-axis followed by x-axis. Z-axis followed by x-axis. So let us write the equation now. Right, as it is x dash, y dash, z dash. What was our formula? We will take our basic formula. X cos theta minus y sin theta. X sin theta plus y cos theta. Okay. So now which should be constant? Y should be constant because we are rotating with respect to y-axis. Now, which axis coming across? First axis, Z followed by X. So all my X should be Z, all my Y should be X. All my X should be Z, all my Y should be X. You understood the order now? This is based on this order. This is based on this order. So, which axis I'm coming across first? Z axis. So, I have to start writing my equation with respect to Z axis first. So, that means it will become Z cos theta minus X sin theta which is the next axis it is coming across? X-axis. My second equation, so this will be Z-axis and this will be X-axis. So my X-axis equation will be Z sine theta plus X cos theta. Is that clear? Now let's see the equation. X dash, Y dash. I'll just wait. You just complete once and then check with my answer whether you could able to write this matrix properly. X, Y, Z, 1. Try to write. So what is my top? So the x-axis, this is my x dash. My x dash is here. So my x dash calculates this part from this part first, right? So what should be my x dash? X cos theta. X is multiplied with cos theta, followed by, I will get y term, which is 0, followed by, I will get z term, which I have to check, sine theta, because in my equation it is z into sine theta. So z into sine theta, 0. So you got x dash, you got x cos theta plus 0 plus z sine theta. Now, what about with respect to y? Y terms remains constant. So that is y comes here. Y is in my second part. So I'll put it 0. First only I can use this. Now I need to check with z dash, which is my equation is this, which actually multiplies with this row to the, again, this column, right? My third row with the xyz1, the column of xyz1. So z cos theta is my first one. Should I need to write a cos theta here? If I write cos theta here, then this cos theta gets multiplied with x, right? So where I should write cos theta? It is z cos theta. My z place is this, cos theta. What is x? X gets multiplied with sine theta, that is minus sine theta. 0, 0, 0, 1. So, which we can write general form. How will I write this? P dash is equal to r with respect to, which one it is? Y of theta multiplied with p. Hope you have understood this. Just 2 more minutes time I'll take to complete the inverse. Okay, this is what this final one. Fine, shall I go ahead? So let me write an inverse here itself, because inverse is similar to your 2D. R inverse of theta is nothing but your R of theta. Okay. When you're doing inverse, because my rotation matrix only deals with cos theta and sin theta. Cos of minus theta, what did I do? This is minus. Cos of minus theta will be a cos theta. Sin of minus theta will become minus sin theta. Which we need to remember. Okay? Which we need to remember. Which we can also say as R inverse of theta is equals to R transpose of theta. So that's with respect to the inverse. So T stands for transpose. T stands for transpose. Fine, it's a simple one. We have already learned in 2D also. And the same thing. Okay.